Worse.
You got it. All right, so we'll start out with Angels. We're working on number 10. So this is 1.7, number 10. Okay. And we've got an RC circuit. And what we're saying is that we've got R equals 5, C equals 1/50th. So we've got R equals 5, C equals 1/50th. E of t equals 100V. And the capacitor is uncharged initially. So that means that Q of 0 equals 0. So Q of 0 equals 0. All right. So let's start out here, Angel. Angel, what was the general solution? So the general solution that you got for the differential equation?
Yeah, so after doing the whole first order linear differential equation thing, I got Q of t equals 2 plus C e to the negative 10t.
Got it. Okay.
So I was right there to see that I was having a bit of trouble. I didn't realize it was Q0 equals 0.
Ah, got it. Okay, so like to be uncharged, that means 0 charge. There you go.
Okay.
All right. So you end up with 0 equals 2 plus CE to the negative 10 times 0. Okay. And so that means C equals negative 2. And so your particular solution ends up being Q of t equals 2 plus or 2 minus 2e to the negative 10t. And there we go. Good?
Yeah. Thank
awesome. You're welcome. All right, next up, we've got 2. 2 said 1.5, number 9C. 2, can you tell me what was the issue that you were having with 1.5, number 9C? Oh, gotcha. Okay. Understood. Okay, I got it. All right. So 2.
Yes, Professor.
Yeah, I am listening. What was the issue that you were having with finding it?
Actually, I have problem when I try to do number B.
B as well, also finding the sketching the slope field.
Yeah, when I find the conservative, the second delivery.
Okay, so finding the changes in concavity as well. You're having a problem with the changes in concavity too?
Yes.
Got it. Okay, so we've got an issue with finding the changes in concavity. Definitely can take care of that. And then we'll also take a look at the predictions that you can make regarding the behavior of the population when P naught is less than T and P naught is in fact greater than T. Okay, so we'll look at both of those. And then I'll help you with kind of like, describing what it is that you might want to say about that. Okay. All right. So I'm going to just mute you right now, and then we'll unmute when after I do some work. Okay. All right, great. So we've got dp dt equals r times p minus t times p, and we're going to find d squared p dt squared. And so that's going to end up being r times, and we'll use the product rule. So the derivative of p is dp dt. Okay, because big T is a constant. And then times p plus, and this will be r again, and then we're going to take times p minus t times dp dt. Okay. Then I'm going to factor out r and dp dt. So this will then be r dp dt times p plus p minus t. And so now this pretty much gives us what we need. This is going to end up being equal to r, and dp dt is going to be r times p minus t times p, and then p 2p minus t, 2p minus t. Okay. So yeah, there you are. So you're changing the concavity, right? And remember, t is constant. It's really important that these population models, they're in terms of only the dependent variable. So consequently, we don't have to worry about like what happens as t changes. All we have just straight across slopes instead of the slope field. They're straight across. And so we just need to consider in terms of p's. Okay. So we've got now our changes in concavity are going to be when p equals t. Okay, because that's p minus t equals 0. It's going to be when p equals 0 and when 2p minus t is equal to 0. Okay. And that means that we are going to get when p is equal to t over 2. And so those are our changes in concavity. If I look here, I will place, right? And I'm going to imagine I got 0 population. I got t, our threshold level, and then I've got t over 2. And so I've got to go in here, and I'm just going to be looking for signs because I need to figure out whether or not I've got positive or negative. So if I'm between 0 and t over 2, then p minus t over 2 is negative. P is positive, and 2p minus t is actually also negative. So that means that these are all positive. So my second derivative there is going to be concave up. They're all positive in that region, right? Because what you have is you have r is a constant, and then you have negative times a positive times a negative, right? Negative times a positive times a negative, and that's all positive. Then I'm going to go t over 2 to t. So p minus, p minus t, it's not p minus t over 2. P minus t, okay, is still going to end up being negative. Okay, p is going to be positive because p is strictly positive in this case, greater than 0. And 2p minus t, okay, is also going to be positive. So the whole thing is going to be negative times positive. So it'll be negative. So concave down. And then when our value is greater than t, okay, then p minus t is going to be positive. P will be positive, and 2p minus t is also going to be positive. So this is all positive. So that ends up being concave up. All right. How's that too? Two.
Yes, Professor.
Oh, sorry. Does that make sense?
Yeah, I'm good.
Okay, great. Anybody else have questions about that? That's finding concavity. And so oftentimes the trick with finding concavity is that we're working with implicit differentiation. So you want to make sure that you're doing that properly. And then it's testing. Now, the thing is with the testing, in this case, and with population models just in general, we only need to figure out values of P, right? But in other cases, more complex slope fields, what you're doing is you're going to be actually determining based upon both P and little t, right? Because sometimes the values of the slope field will change as little t changes, right? Depending upon the slope field that you're looking at. All right. Okay. So now for that second part of your question, for C, I'm going to draw a slope field. And the slope field is going to help me kind of think about, right? So there's 0, p equals 0. And that's actually an equilibrium solution at p equals 0. So I'll do that. P equals 0. It's got this slope field. And here is t. So at p equals t, we also have an equilibrium solution. So make sure you guys get that. I mean, as you're taking a look at this particular problem. So you have an equilibrium solution there. And then we're going to have our changing concavity at t over 2. Okay. I'm just going to figure out basically kind of figure out essentially, well, okay. Well, for the sake of, our conversation, make sure that you do understand this. What we have here is it's increasing above the threshold. Okay. If we look at, it'll be decreasing below the threshold. So it's going to be increasing here above the threshold, decreasing here, below the threshold, okay? And we have our changing concavity. So essentially what you're going to get is you're going to get, you're going to get these slopes. If you're above that threshold, but if you're below the threshold, what you're going to get is you're going to get these downward facing slopes, right? So you can kind of imagine that's what it would kind of look like. So you're kind of drawing a, basic thing. And as you get closer to the equilibrium solutions, everything gets smoothed out because that's what happens as you get closer to equilibrium. So you kind of thinking it looks a little bit like that. So now C is asking us what happens. We're going to consider the cases when P naught is, let's start with less than T, and when P naught is greater than T. So what we'll do is we'll follow our solution curves. So let's say, for example, here's T naught and it's below T. So if we follow this solution curve, we're going to decrease and then we have a change in concavity, right? And then we're going to approach equilibrium. We're going to be going down towards zero. On the other hand, if T naught is greater than T, we're all increasing and also, by the way, concave up, right? So you got this concave up, and that concave up is just going to rocket out to infinity. So this is a big part of understanding what exactly is happening inside of this system with this particular population. So the slope field kind of tells us what's happening with the population. So if the threshold, or if the population is above the threshold, what's going to happen to it? You can put it in the chat, or you can unmute if you like. So if the population is above the threshold, the population will what? Yeah, two? Take a look at what the graph, what's the graph doing? Look at what the graph is doing. Above the threshold, T is the threshold. So if we start above the threshold with T naught, what's going to happen to our population?
The population will go up in rate. Like that.
That's right. Yeah, exactly, Brian. The population will grow without any limit. All right. Now, what about if the population is below the threshold? So we're going to go, if the population is below the threshold, that's where now T naught is below T. Then what's happening there too? Take a look at the solution curve.
The population will decrease, like people dead.
Yeah, it's going to die off. The population will die off. That's what we say, right? Because it's going to decrease to zero. So the population will die off, or we say decrease to zero. So if we think about this, what a threshold is, okay? So a threshold is a limit or a line on which either side of the line, you get two different kinds of behavior, all right? Okay, that's just generally what it means to be a threshold. So on one side of the threshold, okay, we get growth without limit. On the other side of the threshold, what we get is we decline down to zero, or we get die off, okay? Hence why calling it a threshold makes sense, okay? That's the idea. So the threshold is appropriate as a name because on one side of the threshold is growth, and on the other is a declining population to zero. All right. So the idea here is basically like, let's imagine that you're a scientist, and what you wanted to do is you wanted to grow your bacteria cultures. Given the environment that you're in, what you need to do is you need to somehow artificially increase the growth of the bacteria cultures above the threshold. But once you do, the bacteria will grow without you having to do anything to it, right? Or we might imagine, you know, that what you're trying to do is you're trying to terraform a planet. One of these days, maybe one of you guys will get to do that kind of thing. That'll be awesome, right? You're trying to terraform Mars, or what's the one? Titan, right? Okay. You're trying to terraform Titan, and what you need is you need a certain amount of greenhouse gases in order to warm Titan to a place at which life can live, right? Okay. That's the threshold. Once you get past that point, then the environment of the ecosystem kicks on, and you get growth without limit, or up until a different threshold. All right. And so that's kind of the idea. That's the idea that we're dealing with here. Okay. How's that, too?
Yes, it's good, Professor.
Excellent.
Thank you, Professor.
You're welcome. All right. Other homework questions? All righty. Going once? Going twice? Sold. All righty. What we're going to be looking at now is we're looking at something called change of variables. This is 1.8. You got the change of variables. And that's not how you spell variables. There you go. That's how you spell variables. All right. Okay. And so in the change of variables, we're going to be looking at two of them. These are the only thing that we're going to do today. And then we'll do exact differential equations and Euler's method on Thursday. I don't want to get too much farther than the other class that I have, right? My Monday, Wednesday class, and they had yesterday off. So you guys get a light day today. Okay. All right. That was section 1.5. Yes, I. All right. So what we're going to be looking at now is we're going to be looking at a set of equations, and we've got this whole idea of being homogeneous of degree 0. So one of the themes that we've got here, at least with our particular book and doing differential equations, is when do I know when to use certain methods? Okay, so when do I know when to use what we call our change of variables? When to use change of variables. Okay. And so what we're going to be doing, there's a phrase that we use, and it's called being homogeneous of degree 0. And I'm going to kind of simplify that for practical purposes. Okay. Like at what point in time do I know that I can actually use or do something that is homogeneous of degree 0? Okay. Or do I have that? So let's take, for example, let's look at something like this. And we're going to find the particular solution. For, okay, dy dx equals 2x minus y over x plus 4y. And then we got y of 1 equals 1. Okay. And we're going to look at this and we're going to ask ourselves, can I actually use, is this in fact homogeneous to degree 0? Now, what I want to do here is I'm going to divide. So the first thing I want to do is I want to divide by the highest power of, in our case, we'll do it by the highest power of x. Okay. So if you look here, the highest power of x is x. So what I'm going to do is I'm going to take dy dx, and that'll equal 2x minus y over x plus 4y, and it's times 1 over x divided by 1 over x. So we're going to divide the top and the bottom by 1 over x. sometimes you might want to divide by like the highest power of y. So sometimes that might be easier to work with the highest power of y. It just depends. It just totally depends upon the situation. So we'll look at, yeah. So like, and it's kind of hard to say when it is. So just sometimes you want to try it out and go, okay, that looks like it's easier to do with x over y versus y over x. Okay. So now this is going to equal 2 times x over x minus y over x divided by x over x plus 4y over x. Okay. Now the definition of homogeneous of degree 0 is a little bit different from this, but this is a theorem that comes off the definition. So when I rewrite this, this is equal to 2 minus y over x divided by 1 plus 4 times y over x. So because dy dx can be rewritten, and what this is called a function of y over x. Because it can be rewritten as a function of y over x, it is homogeneous of degree 0. And you can use change of variables. So it allows us to actually do that. We can use the change of variables here. So that's our requirement. And you're going to see why in just a moment, because what we're going to do is we're literally going to change our variables. We're going to do a substitution here. All right. So what we're going to do is we're going to let v equal y over x. So v is going to equal y over x. Okay. And we're going to need, in addition to that, we're going to need that vx equals y. Right? That's just a matter of multiplication. So vx equals y. And what we'll need to do, we need to figure out, we need dy dx. We need to figure out dy dx. And that's why actually we need vx equals y. So taking the derivative of both sides, taking ddx of vx equal to ddx of y, or dy dx, right? Okay, and that's all coming from over here, this vx equals y. We end up with dy dx equals dv dx times x plus v. There you go. Sorry. Brain stopped working for just a moment. There you go. And that's just using implicit differentiation. Okay, so the derivative of this side is just going to be dv dx times x plus b. So now what we need to do is we need to substitute in. We're going to substitute into this function. So sub into the original function. So that's going to end up being 2 minus v over 1 plus 4v. Okay, and remember that's equal to dy dx, so that's going to equal dv dx times x plus v. Here, make a change. Just pause for a moment. Any questions so far? All right. Okay. And now what I got to do, what you're going to see is that this is now separable. Okay. This is now separable in x and v. Okay. So we're going to go out and we're going to separate. First, we're going to subtract out v. So minus v from both sides. And then that'll give me dv dx times x equals 2 minus v over 1 plus 4v minus v times 1 plus 4v over 1 plus 4v, right? Just got to find a common denominator there. These are v's. Okay. So this gives me then 2 minus v minus 4v squared over 1 plus 4v. Which is 2 minus 2v minus 4v squared over 1 plus 4v. All right. That's a good question, Ivan. So when we do ddx of vx, you have to remember that v is a function of x. Okay. And so consequently, what we're doing here is we're utilizing the product rule. So we use the product rule using implicit differentiation. So this is the function v times the variable x. And so the derivative of v is dv dx, and then we multiply by x. And then we take v, right, plus the derivative of x. And the derivative of x with respect to x is 1. So this is dv dx times x plus v times 1. And that's how you get dv dx times x plus v. Okay. Okay, so now we've got this. And now what you're going to see is, right, we can separate out. This is all in terms of v. And then we can actually separate out this side. So what we're going to get is we're going to get dv times, and then this is we're going to take the reciprocal here. So it's going to be dv times 1 plus 4v over 2 minus 2v minus 4v squared. And that'll equal dx over x. So just go in, do the separation of variables, do the the math, and basically what you're going to get, you're going to divide through by 2 minus 2v over minus 4v squared over 1 plus 4v. So you'll multiply by the reciprocal, and then you're going to do the same thing with the dx and the x. So we're going to do a little rewriting here. I'm going to get dv times, and then this is going to be 1/2 times, and this will be 1 plus 4v divided by 1 minus v minus 2v squared. Excuse me, 2v squared. And that again is going to equal dx over x. And now that we've separated our variables, what are we going to do? That's it. Alex knows. Jerry knows. Josh knows. Integrate, right? We've now got the opportunity to integrate. Right? Everybody else should know. Once you've separated, you can integrate. So we'll take the integral and we're going to pull out that 1/2. So the integral of 1 plus 4v divided by 1 minus v minus 2v squared dv is going to equal the integral of dx over x. This one actually you can use a u substitution. So we'll do that. We'll let u equal 1 minus v minus 2v squared. So du will end up equaling then -1 minus 4v. And so we want to make that into 1 plus 4v. So that means that dx. So negative du is then going to equal 1 plus 4v, not dx, but dv, excuse me, dv. 1 plus 4v dv. So we get 1/2 the integral, and then this is going to be, we'll pull out the negative, so the negative comes out here. We get 1 over u du equals, and this will be the natural log of x plus c. So this then gives me -1/2 the natural log of, and this will then be 1 minus v minus 2v squared equals the natural log of x plus c. Now remember, when we talked about first order, when we talked about separable, what we want to do is we want to bring that -1/2, make it the power. So this ends up being the natural log of 1 minus v minus 2v squared. Okay, and that's going to end up being to the -1/2. And that'll equal the natural log of x plus c. Then we'll raise both sides to the e power. So this becomes e to the natural log of 1 minus v minus 2v squared to the -1/2 equals e to the natural log of x plus c. So the right-hand side becomes ce to the x, or cx, pardon me, it becomes cx because e to the natural log of x is just x, and e to the c is a constant. So we got cx, and we've got 1 minus v minus 2v squared to the -1/2. Any questions? So basically what we've done is we've utilized the change of variables in order to turn into a separable differential equation, right? Okay, and then we've just done the work, and so far we've done something that's very similar to what we did in, say, like 1.4. Okay, it's basically just in separation of variables. All right, and you'll notice that that's kind of one of those things that you just do a lot inside of differential equations. So now what I need to do now is I actually need to go and change my variables back. See if I can. We'll see if that's the case. Now, I've got it's got 1 over, and because it's the -1/2, it's going to be 1 over the square root of 1 minus v minus, or 1 minus, and then I'm going to change I'm going to remember, let v equals y over x, because that's what our original change was. So y over x minus, okay, 2 times y over x squared. And that's going to equal cx. And I actually think that I'm going to need, in fact, I know I'm going to need this absolute value here. It's not one that we can actually take off. So make sure that you keep that absolute value on there. We're going to keep that absolute value. And remember that y of 1 equals 1. And that's good. This is the easiest place to go do this. So actually finding c right now is going to be a lot easier than finding c later on. Okay. So what we're going to do here is we're plug in 1 and 1 in for y. So y equals 1, x equals 1. So we're going to get 1 over the square root of 1 minus 1 over 1 minus 2 times 1 over 1 squared equals c times 1. And this is an absolute value, remember? There you go. Absolute value. So that means here, if you go through and you simplify, what you're going to get is you're going to get c equals 1 over root 2, which is just simply root 2 over 2. Okay, so now what I'm going to do now is I'm going to solve for y. Now that I have that c is equal to root 2 over 2, I'm going to solve for y. And the first thing that I'm going to do is I'm actually going to simplify the bottom part of this denominator. Okay, so or this one right here. So I'm going to take this and I'm going to make it 1 minus y over x minus 2 times y over x, or we'll call it 2y over x. That's fine. Okay, wait, that's not right. It's 2y squared over x squared, pardon me, because they're squared. And we'll find a common denominator being x squared. So we're going to get this is going to be x squared minus, and we'll multiply by xy minus xy minus 2y squared over x squared. And so this is under the root. I'm just doing this kind of one step at a time. Under the root and in the denominator. That's where that's located. Okay. So what that's going to give me then, I get 1 over the square root of x squared minus xy minus 2y squared over x squared, which is equal to, and this is all on the root, pardon me, is equal to x over the square root of x squared minus xy minus 2y squared. And then that's going to equal root 2 over 2 times x. This, by the way, still in absolute value. So now what I'm going to do is I'm going to multiply. I'm actually going to square both sides. So square both sides, and I'm going to get x over the square root of x squared minus xy minus 2y squared squared equals the square root of 2 over 2 squared. X squared, excuse me, x squared. Which is equal to just then 1/2 x squared. So this gives me now x squared over the square root of x squared, or excuse me, now no longer square root, that's actually just all by itself. X squared over x squared minus xy minus 2y squared, okay, equals 1/2 x squared. We'll divide both sides by x squared. Right, so we'll multiply by 1 over x squared, multiplied by 1 over x squared. And that equals 1 over the square root of x squared minus xy minus 2y squared. And that'll equal 1/2. 1/2. And so now I'll multiply both sides by the denominator there. I get 1 equals 1/2 x squared minus xy minus y squared minus 1/2 xy, excuse me. xy minus y squared. Okay. I think that's probably good enough. This works. At the moment, I got to think about like getting it to y. Two over 2. Oh, okay. We'll just keep it there. Now, on the exam, just to let you know, on the exam, I will let you know if you should keep it implicit, which means keep it as y over x. So keep it implicit, or to solve for y. If you're solving for y, it should be pretty obvious, or maybe not obvious. It'll just take a little bit of work. And I'm talking like hopefully 5 to 10 minutes of algebra tops. In fact, that would be my world. 5 to 10 minutes of algebra tops. If I say to keep it implicit, right? What it means to keep it implicit means don't solve for a y. Because sometimes you'll see some of them, it's going to be brutal. You don't want to solve for y, right? Just the algebra is too messy. Okay. All right. Any questions on the process for change of variables? So the process for change of variables is like the algebra is the hardest part of it. If you're actually going to do the hardest part of the algebra, basically what you're going to do is you're going to divide through by the highest power of x, right? You set v equal to, right? Okay, so like if we're going to write this down, 1, divide through by the highest power of x or y. Depends on which one you want to do. Okay. 2, right? If the DE is homogeneous to degree 0, obviously if it's not, you're not going to do this. But if it's a homogeneous to degree 0, that is that we get a function in terms of y over x. Then what you're going to do is you're going to substitute v equal to y over x, or v equal to x over y. And we'll have dy dx, right, is going to equal, and it's either going to end up being v times dv dx, v times 1, excuse me. So v times 1 plus x times dv dx, or it will be the substitution for v equals x over y. For vy equals x, right? So basically, that's going to be y equals x over v. Yeah. Okay. And so what you just do is you find the derivative of that. So we do that substitution, okay? The result will be separable. So separate and then integrate. So separate and integrate. Find C if appropriate. And then solve for y if asked. And that's it. Okay. Let's take 5 minutes. Let's be back at 11:10. Finish up writing, use the bathroom real quick, get a cup of coffee. We'll be back at 11:10. Okay. All right, come on back in. Okay, so let's take a look at one more example of this general, our homogeneous to degree 0 change of variables. And so let's look at something like this. This is it's actually number 16. So this is 1.8, number 16. And what we're going to do is we're going to see sometimes you're going to have to do a little bit of work in order to actually transform something into homogeneous to degree 0. So in this case, we're going to find the general solution. Okay, we'll find the general solution, and it's going to be xy prime plus y natural log of x is going to equal the natural y times the natural log of y. So that's our DE. So if you remember what we had before, we had something that looked like this. We had something that was like so our normal form, or our standard form, was dy dx equals some function of x and y. Okay, that's our normal look when we were looking at something that's homogeneous to degree 0. So what we need to do is we just basically need to isolate y prime. All right, so our basic thing here to do is to isolate y prime. And so I'll do that. So isolate y prime. And then what you get is you're going to get xy prime equals y natural log of y minus y natural log of x. And then we will, and I'm actually going to factor out that y. So I'm going to make it y times the natural log of y minus the natural log of x. Okay. And I'll even simplify a little bit more. I'm going to see y times the natural log of now y over x. All right, using our rules of exponents. And that's just because I remember that I wanted to be in a function of y over x. And it's like, well, how do you make natural log? Like, what do I do there? I'm not going to be able to divide through by x. So what do I need to do? Well, okay, you know, some rules of exponents or logarithms will allow you to do that. Okay. And then I'll just divide through by x. So I get y prime now is equal to y over x times the natural log of y over x. Okay. Now notice that's homogeneous degree 0 because we have it in terms of y over x. So we don't need to do anything. We don't actually need to like divide through by x because it's already in terms of y over x. So if we let v equal y over x, and then we're going to get then that dy dx, because we did this earlier, was going to equal v plus dv dx times x. That's going to be our change of variables. So we're going to get v plus dv dx times x equals, and this will be v times the natural log of v. Not always, Ivan. Sometimes you want v equal to x over y. And that just depends on the situation. If it's easier for you to like integrate, if you have v equal to x over y, or if like say, for example, if you have higher powers of y than you have the powers of x, then you're going to divide through by powers of y and you end up with x over y. Okay. So it just depends upon how do you get it into a form that will allow you to do the change of variables. Okay. So we can either divide through by powers of x, or we can divide through by powers of y. If we divide through by powers of y, okay, then we're going to end up with v equals x over y instead of v equals y over x. So your goal, if I want to write it, is either v equals y over x or v equals x over y. One or the other. Does that make sense, Ivan? Process is identical though. Okay, process is exactly identical. All right, so now we get dv dx times x is going to equal v times natural log of v minus v. Okay, then we're going to separate. This is now going to be then dv over v and ln of v minus v. And that equals dx over x. And now we've separated. Once we've separated, we can integrate. And I'm going to rewrite this as v times the natural log of v minus 1 equals, okay, excuse me, the integral of dx over x. Okay. And so the left-hand side is actually a u substitution. So we'll let u equal the natural log of v minus 1. So du is going to equal 1 over v dv. And so what we get then is we get the integral of 1 over u du equals, and this is just going to be the natural log of x, absolute value plus c. So this is now the natural log of v minus 1 in absolute value equals the natural log of x plus c, which you'll actually kind of notice that the right-hand side's always going to look like this. Right? I mean, like basically you're always going to end up with dx over x because of the way that we do change of variables. It's just always going to end up being that way. Okay. So we'll take this e to the natural log of v minus 1. Okay. This is, by the way, probably should be an absolute value as well. They have an absolute value? No, they didn't. Equals, and then this is just going to be e to the natural log of x plus c. So cx is going to equal the natural log of v minus 1. Now this one we should actually be should not have too much of a problem solving for y. Well, sub v equals y over x. All right, pause for a moment. Okay, so we get now the natural log of y over x minus 1 equals cx. So the natural log of y over x equals cx plus 1. Take the exponential, okay? And so this is going to give me y over x equals e to the cx plus 1. And then we'll just multiply by x. And so that gives me then y equals x e to the cx plus 1. And that's your general solution. And in this case, we drop those absolute values because once we start solving for y and x, there's no problems with x being negative or with y being negative. If x is negative, y will be negative. If x is positive, y will be positive. There you go. The DE does look like it. The DE would be problematic. It really should. They should have that x and y are both greater than, or that x is greater than 0. That would be the best route. So we should say that x should be greater than 0 because the DE needs to be defined everywhere. All right. Any questions?
When you did the first substitution for v, dy dx was equal to, why was dy dx equal to v plus, is that like implicit? Right there?
That's the implicit substitution. So
Okay.
remember, if you change this around, and this is going to be, it's just the case for all of them. So v, right? Vx equals y.
Oh, and then you differentiate. Okay.
Exactly. It's exactly the same. It's the same every time. So we can also do, you know, just as a side note, I put it into the notes, but if you do this, if you let vy equal x, okay, and we need to solve for dy dx because we've got our terms of dy dx. Excuse me. If we have v equals x over y, okay, let's say that that's the case, v equals x over y, right? Then what we can do here is we rewrite this as vy equals x, okay? And so in this case, this would be dv dx times y plus v equals 1. If we take the derivative with respect to x, excuse me, and v plus v times dy dx. Sorry, I meant to do that. Dy dx equals 1. Okay, now remember that y here, if we take this, y equals v or x over v. So we get dv dx. Probably should have done this the other way around. Yeah, who cares? Times x over v plus v times dy dx equals 1. Just give me a moment here. I go y equals x over v. And what I get is I get dy dx equals x, or v minus x dv dx over v squared. That's better. Okay. I was trying to do it without actually doing the quotient rule. I think this is probably easier. Just use y equals x over v, right? Change this instead of doing it this way. And then this ends up equaling 1 minus x over v squared times dv dx. Just make sure it's as simple as I can get.
Okay, thank you. Makes sense.
All right, yeah. But I just want to give you, make sure that I have the same one that they use in the book for this other one. We use x over y. Okay. All right. Yeah, that's good. There it is. 1 minus x over v squared dv dx is dy dx if we actually go and use x over y. All right. Cool. Let's do the next piece we're going to do here is we're going to be working with Bernoulli's. And this is another kind, it's a different kind of change of variables. Okay. So Bernoulli's actually uses first order differential equations. So it's going to use first order DEs, okay, once we've changed our variable. So the whole point here is, again, to do the change of variable, then use a method that we already know how to use, which is our first order method, okay, and then go back and resubstitute once we get finished. All right, so let's say, for example, what we're going to do, and I'm going to show you how we know, like, and this one is, how do I know? I have a Bernoulli's. So we'll start out with that. Probably a little demonstration is probably the easiest way to do this. What we're going to get is basically, it's a first order differential equation where the right-hand side is multiplied by some power of x, okay? So it's first order, right? We basically have a first order DE, okay? We'll have something like A1 of x times y prime plus A2 of x times y equals, and then this will be some f of x times y to the nth power, where this is actually a power. This is not a derivative, it's a power. N is a power, not a derivative. So if we have something of this form, then what we're going to be able to do is we're actually going to be able to utilize Bernoulli's. So we'll take an example. We'll find the general solution. We got y prime plus 4xy equals 4x cubed y to the 1/2. Okay, first thing we want to do once we have this is we're going to divide through by the power. Okay, so we'll divide by y to the n. And so in this case, that's y to the 1/2. So we're going to get y to the negative 1/2 y prime plus 4x y over, or y times y to the negative 1/2, and we'll get to that in just a second, equals 4x cubed. Now, the reason why Bernoulli's works, notice that when I multiply y times y to the negative 1/2, I get, right, I got y to the negative 1/2 y prime plus 4x y to the 1/2. And what you want to notice here is notice this, is that dy dx of y to the 1/2 is going to equal, we take that derivative, is going to end up equaling negative 1/2 times y to the 1/2, or y to the negative 1/2, excuse me, y to the negative 1/2 times dy dx. All right. And so the cool thing about this is to notice this, is that it's kind of like a u substitution. In fact, it's pretty much identical to u substitution. Notice the y to the 1/2 right there and the dy dx. You see that? That's the trick, right? That's sitting right here. That's the derivative of y to the 1/2. Okay. So what we're going to do is we're going to let u, okay, equal y to the 1/2. Oh, by the way, this equals 4x cubed because we want the other side. But y to the 1/2. So du is going to equal, like we said, it's going to be 1/2 y to the negative 1/2 times dy dx, or y prime. Actually, let's use y prime because we're using y prime here, times y prime. Should, by the way, probably call this du dx, or excuse me, yeah, du dx, because we were taking the derivative with respect to x. So we're going to take du dx equals 1/2 y to the negative 1/2 times y prime. So if I just multiply now, notice just like with a u sub, I've got y to the negative 1/2 y prime. The thing that the extra thing I have here is the 1/2. So I'm going to multiply then by du dx. So we get 2 times du dx times 2 du dx equals y to the negative 1/2 y prime. And now I can substitute. Did I catch that? So basically, more than basically, the your u is going to be, if you actually have a Bernoulli's, your u is going to end up being that power of y. So you'll let u equal, in this case, like y to the 1/2. Then you go, you find du dx, and then you do some multiplication by a constant, and you're done, right? So now we're going to substitute. This is then going to be 2 du dx plus 4x times, and then this is just u, 4xu equals 4x cubed. And what you want to notice now is this is linear and first order. So now we transformed our equation from something that was not linear to something that now is linear. And we can use our linear methods. We'll go in, we'll divide through by 2. So we get now du dx plus, and this will be 2xu equals 2x cubed. So now give us that p of x is going to equal 2 to the x, right? Okay, so I of x, my integrating factor, is going to equal e to the integral of 2x dx, which equals e to the x squared. So now, right, we now get, this is going to give me then e to the x squared times u prime equals 4 e to the x squared times x cubed. integrate both sides. The integral of e to the x squared times u du equals 4e to the x squared times x cubed, and this is, by the way, prime, pardon me, x cubed dx. I'm going to use technology actually to find my integral. Okay. So I'm going to use that symbol that. Here, I'll show you. This is called symbollab.com. It's just it's kind of handy. They've gone to like a pricing model, but it's not actually all that expensive. You can also use Wolfram Alpha in order to do some of your integration, pending, right? For your next exam, you can definitely use this for your integration. Not a problem. Okay. Can everybody see my screen? Cool. Okay. Great. So now I'm just going to go in. I want the integral of e to the x squared, x cubed dx. And there we go. All right. I should have known that. I totally saw that that was the case. Okay, well, whatever. All righty. That's what I wanted. I want to go here. There we go. So that would then give me now, I got e to the x squared times u equals, and we took this integral, pardon me, we integrated both sides. So this will be 1/2 e to the x squared times x squared minus e to the x squared plus c. Divide by e to the x squared. So we get u is going to equal 1/2 x squared minus 1 plus c e to the negative x squared. Now remember, it's substitution. And so we started out with u equals y to the 1/2. So that's exactly what we're going to do. We're going to substitute back in y to the 1/2. So we get y to the 1/2 equals 1/2 x squared minus 1 plus ce to the negative x squared. And then we'll just square both sides. So this gives me now, by squaring both sides, square them, we get y equals 1/2 x squared minus 1 plus ce to the negative x squared, and all that squared. Yeah, this is fine. Right, it's in terms of y. If you needed to solve for c, you could. Wouldn't be all that terrible at that point. So this is completely solved. And that's your general solution. Okay, so let's see. So far, so good. Practice. A little bit of practice will do a lot of good, right? Because the process pretty straightforward. Let's actually just write out what the process is. Okay, right? A a dE of the form right, a1 x y prime plus a2 x y equal to f of x y to the n is a Bernoulli's. So that's our form. We have that form. Okay. 2. We'll divide through by y to the n. And what ends up happening, and you'll see that what ends up happening is we end up with y to the 1 minus n. Okay, so we're going to let u equal y to the 1 minus n. It's basically going to end up being, right? Okay, the value, right? The power of y in front of a2. If you kind of think about it that way. And then du dx, and then we'll let u equal that. We'll find du dx. Call that 4. Okay. And 5, we'll substitute. Six, you solve the first order dE. Okay, so we go in, we solve the first order dE. And then resubstitute for u. Resubstitute for u, solve for y.
Before you integrated both sides, where did you get that 4 from? I was just curious.
This one, the 4e to the x squared times x cubed.
Because I thought we divided by 2.
It's a 2.
Okay.
It's a 2. I was looking at a previous number, so it's a 2. It's a 2. That makes this a probably that makes that probably a 1/4, and that makes that a 1/2, which makes this a 1/4, this a 1/2. Hey, you're looking. I end up looking at something different that's scrolled up on the screen, and then I copy it down as I'm writing, and I just miss. So my apologies. That makes that a 1/4, and that's a 1/2. So you just got to multiply through by 2. You know, when you get into undergraduate math, what ends up happening is at least in the math that I did, you stop using numbers. Where if you use numbers, it's like always figuring out what 1 is. So everything's all variables. And then, you know, you just don't get used to, you're like, okay, oh, those are numbers again. Same thing with graduate school. Graduate school was all like that. And I was like, okay. So when I started back up to get up to teaching again, it was all about bringing the numbers back, right? Getting all the multiplication back, bringing all the numbers back. So there you go. Okay. You'd think since I've been out of graduate school now for like 10 years, 11 years, should have, you know, but whatever. Okay. So let's do one more and then we'll call it a day. Okay. So let's do this one. We're going to do, we're going to find the general solution. And it's going to be 2x times y prime plus y cubed x squared plus y equals 0. Now, we want to think to ourselves, I mean, either this does not look remotely like it's going to be homogeneous to degree 0. So probably it's a Bernoulli's. I can actually kind of tell that because I got this y cubed sitting there. If I got a y cubed, there's a good chance that Bernoulli's might work. So what I need to do is I need to get it in the form of my first order differential equation. So I'm going to do some algebra. And so I'm going to start out, I'm actually going to multiply through by 2x. So I'm going to get 2x y prime plus 2x cubed y cubed plus y equals 0. There we go. Now, if I kind of think about it, I need to get this one over to the other side, right? I need to go over, get it over to my right side. So this is going to be 2x y prime plus y equals negative 2x cubed y cubed. And now it's in the form of one where we can use Bernoulli's. That's the right form. So now that it's in the right form, I'm going to divide through by a y cubed. So this is going to give me 2x y to the negative 3 y prime. Okay, so this is, by the way, divide by y cubed. Plus, and then this is going to be y divided by y cubed, so y to the negative 2 equals negative 2x cubed. All right. Now I'll let you, I'm going to do my substitution. So u equals y to the negative 2, right? It's the one that's in front of the a1. It's not the one with the derivative. U equals y to the negative 2. So du dx is going to equal negative 2y to the negative 3 dy dx. And then just like with a u substitution, I'm going to move over that constant. So we're going to get negative 1/2 du dx equals y to the negative 3rd, and we'll call this y prime. You call it du dx du prime if you want to too. There's no problem there either. So now we'll substitute. We're going to get 2x times negative 1/2. And like I said, we'll call that u prime because it's just du dx u prime plus, and this is going to be u equals negative 2x cubed. Now it's a first order linear DE. It's a DE in U, but that's okay. Doesn't matter. Same methods. So now we get negative x u prime plus u equals negative 2x cubed. And now we got to divide through by negative x. So we get u prime plus, or rather minus 1 over x u equals 2x squared. P of x is going to equal -1 over x. I of x is then going to equal e to the integral of -1 over x dx, which equals e to the negative natural log of x, which equals e to the natural log of x to the -1, which equals x to the -1. Okay. Multiplying both sides through, we end up with now x to the -1 u prime equals, and this ends up being, that's 2x squared, right, times x to the -1, 2x squared times x to the -1, which just equals 2x. Beautiful. Integrate both sides.
I think the right side's supposed to have a negative.
I divided -2x cubed by -x, and that's where the negative
Oh,
went.
yeah. Just can't.
Thanks, Josh. All right. So u ends up equaling x cubed plus cx. So hopefully you're feeling comfortable. Let me know if you have any issues with the first order linear. This is finding the first order linear, but definitely the kind of thing that practice makes perfect on. Okay. Any questions? All right. 30 seconds, let people kind of, all right, do I get it? Do I not? So now we're going to go in and resubstitute. We're going to resubstitute. So you remember that u equal to y to the -2. So we've got y to the -2 equals x cubed plus cx. So if we rewrite this, we're going to get it 1 over y squared equals x cubed plus cx. So what that means is that y squared is going to equal 1 over x cubed plus cx. And so y is going to equal the square root, or 1 over the square root of x cubed plus cx. And that is your general solution. Questions? Okay. So on Thursday, right? The next time we meet, Thursday, we will be doing 1.9 and 1.10. And then we're done. Then the entire chapter is finished. We're done with chapter 1. Okay. The first exam for this is not this weekend, it's next weekend. Okay. So, you know, make sure that you get all caught up this weekend, that you've gone through and you've done your homework, that you've got any questions that you need to have asked, so we can ask them in class on next week or in office hours. Okay. Does anybody have, okay. And then office hours, I have office hours here from 1 o'clock to 3 o'clock. Do not forget that if you would like to come in, just send me an email. That way I can turn on my Zoom, and I will turn on my Zoom within a couple minutes. Generally, it takes me a minute or two before I get the email. Okay. All right. So on Thursday, right, you want to watch your videos for 1.9, that's exact differential equations, and 1.10, which is Euler's method. Okay. Euler's method looks a lot like slope fields. So, you know, hopefully our understanding of the slope fields will be fine. You'll be fine, Knock, but it will be fine. Just practice, study, right? Understand what it is that we're doing, right? And you should be great on your exam. Your exam will do great. All right. Well done, everyone. If you need me, come see me at 1. Good. That's dismissed. Have a great one.
Professor, a quick question. So I was able to fix my email now.
Oh,
so
great.
what exactly do you need me to give you?
I need you to send me just your student ID number, like the one that I should use, the one that represents you as a student. If you can do that, then you're all good to go.
So I mean, for my student ID, it's still the same number, but it's under a different email.
I mean, okay. What I mean is that the web advisor ID that you use for email.
Oh, okay. Okay, sounds good. Thank you. I'll send you an email then.
Perfect. That'd be great.
Okay, thank you. Bye-bye.
You're welcome. Bye. Ivan, it is not during class time. It's actually going to be over the weekend. You have from Friday to Sunday to do the exam. You're welcome, everyone. You're welcome. You're welcome. Angel, see you on Thursday. You all set, Nathaniel? Oh, there he goes. He's off. And we'll see you later, too. Oh, 2. Question. Are you there?
Yeah, I'm here.
Good. Question. I had a question about what exactly you were asking in your email. I wasn't sure what the issue was. Oh, hold on. Let me first.